Hello again, grade 11s, and welcome to another example involving or on electrostatics. Here we are again looking at a problem involving the net electrostatic force. But here we're going to have vectors in two dimension. So you need to think about everything you've learned about vectors in two dimension because we're going to incorporate it into this problem. They say there are three charges, Q1, Q2, and Q3, which are placed as shown in the figure. Calculate the net electrostatic force that is exerted on charge Q. So the focus here is Q2, and this force is exerted by Q1 and Q3. Let's analyze the diagram. Firstly, we need to change our values to the correct SI units. Q1 has a charge of -2 microcoulomb. That means the same as -2 times 10 to the -6 coulomb. Q2 has a charge of +1,5 microcoulomb, which means the same as 1,5 times 10 to the -6 coulomb. Q3 has a charge of +1,8 microcoulomb, which means the same as 1,8 times 10 to the -6 coulomb. The distance between Q1 and Q2 is given in millimeters. So we convert by dividing by 1000 or by multiplying by 10 to the -3. Exactly the same thing applies to the distance between Q2 and Q3, and this distance means the same as 30 times 10 to the -3 meters. Please always make sure that you convert to the correct SI unit, because if you do not, you're going to end up with incorrect values and you're going to lose marks for your substitution and for your answers. So now that we have looked at this, we are looking to see what the net force is on Q2. Like in the previous problem, whenever you're asked to calculate net force, always start off by drawing a free body diagram. We look at only one of the spheres, so now we see what is Q1 doing to Q2. Q1 is negatively charged, Q2 is positively charged. We have opposite charges, which means that Q1 is going to pull Q2 towards itself. And therefore, on the free body diagram, we're going to include the electrostatic force of 1 on 2, and that's going to be towards the left. Now that we're done seeing what Q1 does, let's look to see what Q3 is going to do to Q2. Q2 is positively charged and Q3 is also positively charged. We have like charges, and we know that like charges repel. Now be careful here. If Q3 is at the bottom and it's pushing Q2 away because they are repelling, it's going to push Q2 up. So on the free body diagram, we go and draw a vector upwards, an arrow upwards, and this is the electrostatic force of 3 on 2. These are the two electrostatic forces on Q2. Now that we have our free body diagram, we can focus on finding out the magnitude and perhaps the direction, which we've actually already done, of these individual forces. Let's start off with the electrostatic force that sphere 1 or charge 1 exerts on charge 2. We're going to use Coulomb's law to perform this calculation. And we're going to divide, please, by r squared. Don't forget that square. K is given to us as 9 times 10 to the power of 9. Q1 is given as -2 times 10 to the -6, but oops, I made a mistake. We do not substitute negatives into this formula, so please don't be careless like me. Make sure to only plug in magnitude. The charge on Q2 is given as 1,5 times 10 to the -6. We're going to divide this by the distance between them squared, which is 20 times 10 to the -3 meters, and we must square this value, please. When we plug this into our calculators, we find out that the magnitude of this force is 67,5 newtons. And since we already found out the direction, we can simply write down that this force is to the left. Now we can move on to the force that 3 exerts on 2. So all that is going to happen is instead of plugging Q1 in, we're going to plug Q3 in. We have the proportionality constant. It's 9 times 10 to the power of 9. Q3 is this value, which is 1,8 times 10 to the negative 6. Q2 still maintains its charge of 1,5 times 10 to the negative 6, and we're going to divide by the distance between them squared, which is 30 times 10 to the negative 3, and as normal, we don't forget the square. When we plug this into our into our calculator, we end up with an answer of 27 newtons. And since we've already drawn the free body diagram, we know that this force is going to act upwards. So we write here, up. Now we have a bit of a problem. See, we would like to calculate the net force, but we're not allowed to calculate or add together vectors that are not parallel to each other. And here we have one force acting left and one force acting upwards. So as mentioned at the start of this video, we're going to have to use what we know about vectors in 2 dimensions. We start off by using the tail-to-head method to, in a sense, add these forces together, right? So the first force, the force of 1 on 2 is to the left. To its head, we're going to attach the force of 3 on 2, and that is a force upwards. That's the force of 3 on 2. You'll notice that once we have added the forces together, we do not have a closed vector diagram because we do have a resultant here. We do have a net force. To find the net force, we go from the tail of the first vector and we draw in an arrow from this tail to the head of the last vector. So now we go and draw in an arrow. These arrows do not need to be to scale because we are using this diagram to guide us. This over here is going to be F net, the net force, the net electrostatic force. This is a right angle triangle. We know the force of 1 on 2 is 67,5 newtons. The force of 3 on 2 is 27 newtons. We're looking for the hypotenuse, so we can simply make use of Pythagoras' theorem by saying that the net force, F net, which is the hypotenuse, is going to equal to the square root of the sum of the sum of the squares on the other two sides. So we take 27 and we square it. This is F3 on 2. And we take 67,5 and we square it, and we take the square root of that. When we take the square root, we find that the magnitude of the net force is 72,7 newtons. Now, this is only the magnitude of the force. We still need the direction. We normally measure direction from the tail of the force. So we know we're looking for an angle over there. And if we draw in a Cartesian plane here, there's our y-axis, there's the x-axis. So let's find out what theta is. We have all of the sides now, but I'm going to use this side and that side. This is opposite the angle, this is adjacent to the angle. So tan theta is going to equal to opposite, which is 27, over adjacent, which is 67,5. We shift tan 27 over 67,5, and we find out that theta is equal to 21,8 degrees. This gives us the direction, but we must explain the answer fully. So we say, therefore, the net force is going to equal to 72,7 newtons at an angle of 21,8 degrees above the negative x-axis. Because on this side over here, we have the negative x-axis. Here's positive, there's negative. And this theta is measured above the negative x-axis. This is the answer to this question, which required us to calculate the net electrostatic force. And we are therefore done with this example.